Tom Black and Dave Sappington, they're doing some science, working with Professor Murphy and some of his team, doing some science to do a look for pointing errors with the telescope. They're going to talk all about this stuff here. Both engineers, one's an aeronautical engineer, the other one's a software engineer. It's a funny story though about this picture here. So about 2 seconds before I took this picture of them, I said to them, hey, this seems like pretty technical and pretty science stuff. Maybe I can help you with this. And then I took the picture. And you see that little smirk on Thomas' face, like, yeah, yeah. And Dave's like, oh, here we go. So in any case, tonight we have a great presentation from them. And who's up first?
I think I am.
Who's going to kick it off? I'll take it.
Yeah.
Thank you.
Verify, make sure people can hear all the stuff here in the back.
Is this the first slide?
No, there's a title slide.
Back to the beginning.
You're on slide 14.
That. Let's go forward, but not, there we go.
There we go.
Magic touch.
All right.
There we go.
Yeah.
Okay.
Didn't spoil the presentation.
You're going to drive. Yeah, you can drive. Yeah, no, that's fine. You can drive. We're not going to stand here. Wow.
We can do that, back you wherever, so.
Yeah.
I'd like to stand.
I guess this is
This
fine.
is being shared online, so it doesn't matter. You don't have to stand in front of it.
Yeah. Why don't these guys just see? So I'm Dave Sappington. I'll kick it off. Tom Black will take over a little later on, and then I'll come back. We'll kind of tag team it here. So at any rate, we're going to talk about the McCormick Observatory telescope, which is right behind us, and you probably saw it on the way in, and pointing errors associated with it. So next slide. So first, some of the specs for the telescope. It's 26-inch aperture. You probably heard that mentioned a lot of times. We just say it's the 26-inch telescope as opposed to the 6-inch in the doghouse. It has a 10-meter focal length, which gives it a focal ratio of f15. So it's not as good for deep sky diffuse objects, but it's exquisite for high precision astrometry work. It was used, Boris, who's not here, did parallax measurements back in the day. So that's done, and it's great for looking at planetary. So it excels at high power things because of that, the extended reach of that big long focal length. It's got a big beefy German equatorial mount, which you saw when you came in. That thing's ton. I don't know how much it weighs, but probably a lot. And it has sidereal tracking. I'm not aware that it can track at lunar or solar rates, but there's really not a need to. It can be slewed by hand, which is often what you do, especially the kind of the old timers and guys that know what they're doing. They could just, I know Boris just whips that thing around and finds stuff. Ed did it the other night. He's really good at doing that. You can also slew it kind of with motors. It has a motor on the right ascension axis, but it doesn't have a motor on the declination axis, though it does have a motor on a tangent arm, which is think of it as fine declination motion. So when you want to slew around to something that's at a substantially different declination, you have to rotate the scope around so that you can reach it by hand, and then slew it by hand to get you in the ballpark and then go from there. You'll see kind of evidence of that later when we talk about the points we get. It's easy to collect points if you pick a declination and then you just kind of get a bunch of right ascensions at that, because it's easy to move in right ascension, not so much in declination. It has encoders on both axes of 400K pulses per revolution, which works out to about 3 arc seconds per pulse. So an arc second is, of course, 1/3600th of a degree. So pretty fine. It's got an additional encoder on the declination tangent arm because the declination tangent arm and the declination axis together tell you where you're pointed in declination. So next slide. So what's pointing error? As always, when we talk about something, what precisely do we mean by this? Basically, in a nutshell, it's the difference between what the telescope reports where it's pointed, and there's an LCD, a display panel on the telescope's main pedestal and also a satellite one near the eyepiece that tells you basically a lot of information, but this last particular one is the right ascension down there with hours, 20 hours, 10 minutes, so forth, and plus 36 degrees declination. So it tells you where it thinks it's pointed based on the encoders. And what we did is we put a camera at the end, took pictures of various star fields, used astrometry.net. You can either upload to it or you can download the stuff, and Tom can talk about that some more, but use astrometry.net to basically take this picture, look it up in a database, and say, what is the center coordinate of this picture? And it gives you the center coordinate, and then you can compare those. Now, it's a little bit more complicated than that, and I'll talk about that because there's some pre-process or post-processing you have to do to this to get these to be apples and apples. But in a nutshell, it's where the telescope thinks it's pointed versus where it's actually pointed, and we're trying to reconcile those. So if you go to the next slide. So why do we care about doing this? I care because when I started trying to use the 26-inch, and I'm not fully vetted, so there's always somebody around me when I'm doing it. I found it frustrating because I'm coming from a computer background. It's like, well, here's where the thing is. This is the coordinate of it. Maybe I'll convert it from a standard coordinate to a current coordinate, and let's just put that on the dial, and we should be able to look through it, and it's there, right? No. So the field of view of the 26-inch, even with the widest field eyepiece, is relatively tiny. So about 16.5 arc minutes. And for scale, this would be about the diameter of the full moon. So, a little bit less than half the diameter of the full moon is what you're looking at through a soda straw at the sky and try and find stuff. And it does have a finder scope, and people that have used it for a while, and Boris and others, seem to have no problem finding stuff, but it was frustrating for me. So it's like, we got to do better than that. In particularly, when we start using cameras, the ASI 2600 is a relatively large field camera. There's a bigger one. I think it's called the AP. It's the compact size of a 35 millimeter sensor. That's the size of its sensor on that scale. So if you punch in the coordinates for the M13 globular cluster, the telescope will point here. And then you'll say, where is it? Search around. And while it might be easier to find a big glob like this just by kind of moving it around, when this isn't so big, as if it were a double star, then it's a pain to kind of move this around to find it. And especially this smaller one is the planetary camera that we're currently using to do some double star work. So it's a real challenge to find this with that to try to slew around. So that's basically the motivation. So the next slide. So what do we do about it? And this is a very high level view of what we're going to do about it. We're going to characterize the sources of this pointing error. We're going to gather a bunch of data, which are basically tuples of what the telescope display read and what the plate solved coordinates were. Then we're going to take we're going to remove the well-characterized aspects of those plate-solved coordinates, and I'll talk about that later. And then basically, we're going to build a mathematical model that accounts for the remaining effects, which is essentially a mathematical model of the telescope and the mount, where it points in space. So next slide. Okay. So I'm going to hand it off to Tom to talk a little bit about the history of the scope.
All right.
Oh, hold on, Tom. Or you got one.
No, I've got one. Thank you. Yeah. So just to kind of put all of this stuff about pointing error in context, it kind of helps to understand, this is an old scope. It was operational in, I believe Ed said 1885. And of course, that predated electricity. Now, as Dave was saying, the field of view of the scope is very small. And so you have the problem that you need to track the Earth's motion. to keep your target in the field of view. Well, how did you do that before electricity? Well, essentially you had something like the weight system from an old grandfather clock on a larger scale.
And that's fine, maybe.
And yeah, so here we go. Yeah, there we go. And this was the governor mechanism that was connected to those descending weights that move the telescope with the Earth's motion, so that you could even without electricity available, that you could keep a target precisely in your field of view. And at that time, there was no display. You read the scope coordinates off of the gearing on the scope, and we can look at that out there if you would like to afterwards. So you would manually move the scope where you wanted to be. You would and then clamp down the scope so that the only motion is tracking the Earth. Next slide, please. Now, also the dome was operated manually. There's still a mechanism for doing that. So if we lost power, it still works. It takes a bit to crank it around, but it and then this structure you see here, sort of a stair ladder thing with a seat. This also dates back to the origins of the scope, and and the need for it is that if you are pointing at something relatively low to the horizon, the end of the scope is now 20 feet or more above the floor. So you have to you have to get up higher to look through it in that situation. It's very clever. The two ropes in the middle here raise and lower the seat, so you'll be sitting on it and pull yourself up and down. The ropes on either side move it around, and it's actually on a rail, on a circular rail, so you can move yourself all the way around the room on that. And so this is still in use, and so we can go ahead and move on. All right. Well, it was in 1963. Was the first really major upgrade to the system. They installed motors to move the scope, removing the old weight-driven system, and this is the original control box for it, and it was basically hardwired logic in terms of, there's no computer or software involved. It was, but there were apparently some reliability issues, failures of relays and motors and so on. But it was used for quite a while, but it was replaced in 2007. Go on to the next slide. This picture here shows the inside of the current control box, which is on the back end of the scope facing the door you all came in through. And it's interesting because even though it was 2007, the person that built this built it essentially with older logic, older hardware, and it's mostly discrete logic. Again, there's no software or computer running this, and it has proved to be very reliable. This is the control box, and you can power on and off, tracking on and off, a switch that opens the cover on the scope, and then these are the buttons for clamping or unclamping right ascension and declination. And these allow motion in right ascension and declination. Now, you only have a slew motor in right ascension. Declination has to be done manually, but you can move slowly in declination using these controls. You can only track for the way the system is designed, you can only track for 90 minutes at a time. And then you have to do a sector reset to reset the tracking system back to a starting point, and then you can do another 90 minutes. But that's the longest single duration you can do. Oh, but one more switch for moving the dome. A little more convenient than turning a crank. Back up just one bit more, and then again, this is the display system. And this display is controlled by a separate computer. So this is the first time you have some software involved. And that computer is reading the encoder outputs from the two axes and calculating the position from that. And and it's showing the local sidereal time, the hour angle, and then the position of the tangent arm. And then at the bottom is the right ascension and declination. And you'll notice that if you add the local sidereal time to the hour angle, you get the right ascension. So typically, I think in the past, I believe there's actually a dedicated clock that had local sidereal time here that they used to get them to because what you read off the scope is the hour angle. So if you know the hour angle and you know the local sidereal time, you can figure out the right ascension coordinate. Next slide. So right now, to operate the scope, you unclamp right ascension and declination, turn on tracking, move the scope manually in declination to as close as you can, clamp declination, and then you use the slew motor for right ascension to drive it to your right ascension coordinate, clamp that. Then you're in a position to do some fine tuning. And usually because of the kind of error that Dave was showing, usually you're not in the field of view of the main scope initially, and you need to go and look through the finder scope, center your target there, go back to the main scope, tweak it some more. So anyway, going on from there. All right, and I'll turn it back over to Dave to talk about the pointing error sources. Yes.
So you need to know your coordinates for the target before you. This isn't a go-to type.
No.
No, it is not a go-to scope. Yeah.
If you know where it is in the sky and you're good at manually pointing it, like Ed is and Boris and some of the others, well, they go to it, it's amazing, but yeah.
It's something like a deep sky object if you're trying to find that.
Yeah, I remember we were looking, Boris and I were looking for a galaxy once and we couldn't find it because it's hard to find. I think partly it was way high in the sky, and when you're looking straight up almost with the scope, there are other challenges physically with this thing. It starts running into the pier if you get too close. But at any rate, I want to categorize the pointing error sources that you might see. And I'll just I somewhat arbitrarily broke them into 3 categories here. This telescope and mount is one source of things, and that's actually going to be the focus of what we're trying to figure out. But to be able to do that, we need to account for some of the other things that are also in play. One of which is atmospheric refraction. That's not a huge concern, but I'll show some information about that. And basically astronomical effects, most notably precession and nutation. I will note that, and I'm not sure about this, and maybe Ed knows, but this telescope has been in operation for 150 odd-ish years, 1885-ish. So the position of the north in the sky is, can change over those time frames. I guess we're at the same latitude, so maybe that doesn't change as much, but if there's logic in there, there's definitely a difference between the coordinate system then and now, which I'll get to. So let's go to the next slide.
Dave, I'll stop there. Just
Okay,
to mention
go back.
The cool thing about precession is because the Earth is precessing.
Yeah,
And the telescope is mounted on the Earth.
it doesn't.
So as the coordinate system changes, you don't have to worry about the telescope becoming unaligned with.
Yes.
They both precess together.
I came to that realization.
Yes, it took a while.
Yeah.
The pier settling and things like that.
Yeah.
Cause it to change.
Yeah,
But they'll precess together.
yeah. Good that you pointed out, because I was saying that, I'm like, that doesn't make any sense. Thanks for that, Ed. So atmospheric refraction, Tom found this book, Astronomical Algorithms, which is kind of handy. And basically what they did in that book is they fit a curve to, I guess, a notional atmosphere, because, they had to make assumptions about temperature profiles and things like that. So
I think there's a temperature and pressure adjustment to it.
Yeah,
Take it that
yeah,
way.
but I didn't use it that. This is a question whether or not you did it. So Tom did much of the math in this thing, and I did it kind of independently, some of the math. So I just applied the formula given in here that relates elevation angle to atmospheric refraction. And the effect is, when you're looking straight up, there is none, because there's no, the different, it's kind of like looking in a glass of water. If you have a pencil in it, it looks pretty much straight down if you're looking at it dead on. It's only when you look at it kind of slanted that there's an issue. But in general, these low elevation angles, you're not going to want to use that 26-inch. You are way, way up on the pedestal to look at it there. So I don't know, the lowest we've gone maybe is.
And even there, it's only a couple of arcs.
Yeah, so this is relatively small. I think I can't remember how the lowest we've gone on that. It's probably maybe 25 degrees or something like that. So, only a couple of arc minutes at that. So this isn't a big thing, but we put it in there. Next slide. So precession and nutation are larger things to account for. And the reason we have to account for these is they change, first of all. And actually, they're due to the motion, to the effect of the sun and the moon's gravity on the Earth. The Earth is spinning like a top, and you get these differential tugs that, the new spin has got to be a kind of a vector sum of the angular moment and all those gravitational forces, and you get wobbles. So if you maybe go just momentarily to this, I thought it was a cool animation by, no, not that slide, the precession and nutation animation. This is something by NASA Goddard. I thought it was pretty cool. So this is kind of the location of the fixed stars. And you see that the precession, it takes about 26,000 years to make a circle around that. And the nutation is a kind of finer motion with cycles. I think the characteristic cycle is about 18.5 years, but there are a bunch of cycles overlaid on that. But the net effect of all those things, you can go back to the main slide then, is that and I like to think of it this way, I'll pick my trusty Earth right here. And as you can see, right ascension and declination are equatorial based coordinates. And so if there's something in the sky up there, the coordinates that you see for that sky are going to depend on what this thing is pointing at. And I've just said in precession and nutation, this thing is, it's actually wobbling around like this, but there are final motions like this along the way. And so if this axis changes, then everything in the sky, the coordinates of which change as well, because the coordinates are based on, where this thing points. So the upshot of all that is star catalogs and things like that have to basically pick a date if they're going to give you the coordinates of the target, because the coordinates of the target depend on when you're looking at it because of that. So typically, the published coordinates use a well-known time. associated with J2000, kind of where the equinox is. It's sometimes called an epoch, but it's I guess more precisely, refers to where the vernal equinox is or whatever. I'm out of my league here, so I'll just probably leave it at that. And it's based on a time of January 1, 2000 at about noon. It's a couple minutes before then, but about noon UTC. And then from that, you can use existing tools to take it from that epoch into the current time. We call it J now. And that's important because presumably the telescope display is displaying the coordinates in what I'll call the J now system. These are the coordinates as of now and where the Earth is pointed now. And we have to compare those with published coordinates that were the coordinates associated with the year 2000. So we have to do some conversions of that. Next slide.
Quick question. On that precession, right?
Mhm.
On the globe here, what is the time it takes to do a complete?
Yeah, so this is
26,000.
about 26,000 years. So, right now, the pole is pointing to Polaris, about 14, near Polaris, yeah, within about a degree of Polaris. About 14,000 years from now, it will wobble around and point close to where Vega is. And then another 12,000 years, it'll come back and point to Polaris. I think it may be actually moving away from Polaris now. Once looked at it, I can't remember, but it's in the vicinity of Polaris right now. Next slide. I hadn't found this online, so I said, what the heck, I'll just make a picture of it myself. So I did some computations. So the underlay of this, which you probably can't see because I can barely see, is a sky map. The constellations, here's Orion, Gemini, Leo, various other things. And this gives you a notion of the difference in coordinates between, for instance, J2000, which is the published thing, what we use our star catalogs, and that's what the astrometry.net gives us, and basically now, J2025. And this isn't what I use to compute things. This is just a visualization that I produced that gives you some notion of it. The max difference is along the ecliptic, and it's 20 couple arc minutes. An arc minute, again, is a 60th of a degree.
And again, to reference, the moon is about 30 arc minutes across.
Yeah, so
So
the difference right about here, which is on the order of, I think it's about 22. The effect is about 50 arc seconds per year. If you want to do the math, and 25 times 50 arc seconds is 22 minutes of arc. So the effect is along here, the difference between what the J2000 coordinate tells you in the sky and what the current coordinate tells you in the sky is just a little bit less than the diameter of the full moon, which isn't a lot, but that's more than the soda straw of the field of view that you're looking through with the telescope. So it's significant.
Dave, so how often are you going to have to change that differential?
So the differential computed on the fly. This is just a visualization of it at a given J2025. In practice, nowadays, since there's computer software to do it, you just put in the date and time of your observation, and it'll compute it from then to, from J2000 to J now. Like I said, this was just a visualization that I created to give you a notion of the scale of it. I mean,
It's been 25 years then since the map was set up. 25 years?
well, so I mentioned J2000 because that's what most published astronomical coordinates use. If you're going to write it down, you have to pick a time, to write it down, and the time is usually 2000. If you were to, I did it for fun, if you did it from J1885-ish when this thing does, the effect is much greater. It's about 2 degrees along the ecliptic for that. So, it moves about a degree every 71 years or so.
That's what I was trying to.
Yeah, so that's an effect. So a diameter of the moon every 35 years or so. So it's significant over sufficiently long time scales. And since things are published in J2000 and we read in J now, we've got to do that conversion. Otherwise, it'll swamp our error budget. So if you go to the next slide. So basically what we do, just kind of in a nutshell, is we take the original image that a star field that we take with the 26-inch. We plate solve it using either an online system, or Tom does it, you can pull down stuff and do it an offline calculation. That gives it center coordinates in J2000. And simultaneously, it's kind of clever, we put a little iPhone up and captured a movie of the telescope LCD display while we were doing that. And then the images are time-stamped, and you compare it with a movie timestamp, and you could align them up. But you plate solve to J2000, you convert the RA deck to JNOW. So you use the specific date time of the image, not just a specific J2 2025. You convert to alt-az because atmospheric refraction is a function of the azimuth, or I'm sorry, the altitude angle. So you need that. So you get that, you apply it, and the effect is that changes things a little bit. And then you back it out, so you apply the refraction, you back it out to JNOW coordinates. And now you have JNOW coordinates that you can reasonably compare with the display that's on the telescope, which brings us to the next slide, which I think is probably where we'll hand off to Tom.
Okay. So in researching this, I was looking at a variety of different models for solving this kind of problem. This problem is not unique to this. I believe UVA at its other telescopes has pointing models for doing corrections on their working scopes. Is that correct, Ed?
Sorry, we were having a separate conversation. So what was that, Tom?
Just that you do use pointing models for your existing scopes at Fan Mountain and so on. So this is, yeah. And I just happened to, I found a paper that that I thought did a really good job of defining a model that was reasonably sophisticated. So if you download the presentation and want to look at it, you can click this link and it'll take you there. Next slide. The model takes into account certain errors, like what is the polar misalignment of the scope? Well, what's the misalignment between the right ascension and declination axes? Is the primary mirror misaligned? Are there errors, calibration errors in the encoders that are reading your position, so on. And then there are some other effects that aren't explicitly part of the model, but that are handled in a more general form, that if you've got enough data to represent the variations in data with pointing direction, even if it's not part of the scope mechanics, the math will adjust for it. And that would include effects from gravity bending the scope, and also thermal effects. Gearing backlash, that's one that we haven't, I believe that's probably something that does exist, but I'm not sure how we easily quantify that. Frequently when you're changing directions with gears, there's some slop in them and so on. But if you're it shouldn't be too much of an issue if you're just in a tracking mode and you're moving in one direction. That should not be a minor effect. Next slide. All right. So the thought with gravity is just, well, you got this really long tube, and if you're pointed straight up, well, it's not an issue. But if you're looking at something low to the horizon, the weight of the scope is going to tend to bend it on each end. It's going to tend to curve it a little bit. Next slide. That's, haven't really, have not actually quantified that. And actually, it should be possible to estimate that, but I don't think we actually did that calculation. We're just kind of
Yeah.
relying on the mathematics of the model to take it into account. Anyway, next slide, please. Also, then we have, there's a small effect. These are all relatively small effects. Thermal effects. Well, okay, let's say you have a small error in your optical path because of a misalignment in the primary mirror. Well, okay, now, now go to really cold temperatures and your tube contracts, and that contraction is going to tend to amplify whatever pointing error was there. So you would expect to see an effect from temperature. Okay. Next slide. All right. And actually, I will show that we saw both of those things in the data. But first, I want to start out with where we looked. This is our grid on the sky of points that we took. And this was done, we did this in June, August, December, and January 4th. Okay. And generally what we would do is set a declination value for the scope and then walk to different right ascension points, which is why you are seeing lines like this. Now, next slide. This is the same pattern of points, but this time, instead of looking at it in terms of right ascension declination, this is in terms of altitude or I mean, excuse me, azimuth and elevation. And there's a couple of things to note is that there's certain parts of the sky are not accessible because we can't do a meridian flip with the scope. There's some safety concerns associated with that. So these bands on either end are not really accessible. However, again, what we have here is we'll set a particular declination and then do a range of right ascensions, and you can see how the pattern shifts as you go out. But so you end up getting a sort of an arc, and yeah, and it looks like we had one point at 10 degrees. So anyway, okay, next slide. Now this is where we actually did observe effects from gravity bending and temperature, okay? And there's quite a bit of scatter here, but this is high elevation pointing up, and you see the lowest errors, and then as you progress to lower elevations, you see the error grow significantly. You know, there's quite a bit of scatter, but there's your curve fit. Now that curve fit is just for the first set of 3 observations we did. It got weird in January, okay, because that set we started at, it was 32 degrees when we started, and it was 22 degrees when we finished. And that group of points at the very top were at 22 degrees. Okay, so now you still see the same trend line, but it seems that when you get below freezing, there is a strong temperature effect in the pointing error. So
for June, the green dots there, it looks like at least on June 24th, you know, tilting it the
effect was small.
Small, yeah.
Yeah, yeah. So it's but you know, at least there is an observable effect. Now one thing I will say, we went with all of this data, including the very cold data in the run of the model. There are, you could argue that you shouldn't include it because it was anomalous and, in one sense. But on the other hand, then you'd have a big hole in the sky coverage and you'd have fewer data points, which, the more data points for the model, the better. So we've run it with this. It might be something as a future thing to return to when we have some warm weather again, to repeat, to pull that set of data and replace it with some data that's more in line with this. So anyway, next slide. All right, results from the model. Without the model, just as the scope as it is now, we were seeing an average of about 7.5 arc minutes for a pointing error with a maximum of about 17. So, generally speaking, you were not going to hit your target in the field of view to start with. With the model, it's reduced significantly. It's about 1.2 arc minutes. And the maximum we saw was about 4 arc minutes at that point. So a significant improvement. I suspect that if we did go ahead and replace that very cold temperature data, that we could improve this a bit more. But, more data would help too. Now, as far as other things that come out of this, we do see polar alignments and misalignments of a few arc minutes coming out of this. There is apparently a significant deviation between the right ascension and declination axes. And then this is very interesting in that there appears to be a misalignment of the primary mirror that's about half a degree, but there's an hour hour angle encoder offset seems to balance it out. So that's essentially canceling out the effect. And then there's also a declination error. So now we could, again, the sigmas on this, some of this are pretty large. More data is better. We can always improve it. So next slide.
Can I ask you a question? So if I had that information and I'm shooting for a particular object and the angle is 45 degrees,
Mhm.
the temperature, can I actually use that and then say, okay, I know what the offset should be and adjust for it? Or is that, in other words, can I then more accurately point?
Well, you could do sort of, you could set it up so you had software that would say, this is the coordinate I want to go to, but here's what I have to correct it to actually make it work. You could do that now without touching the scope or doing anything at all, okay? What we've been discussing with Ed, though, is taking the results from this pointing model and including it in the software that drives the scope display. So that's where we want to go, so that you don't have to do the extra calculation, that the computer that's driving the display will do the calculation and give you this instead of that. Okay? Yes.
Would it make sense to have a temperature-based change?
Well,
22 degrees.
actually, now that you go next slide. Let's go one more. We'll come back to this. One more. I talked a little bit about things you could do. You could go ahead and have a warm temperature model and a cold temperature model, and if you wanted to go crazy, you could put a thermometer out there that runs into the computer and actually decide how to interpolate based on the temperature.
Well, I guess I was suggesting
Yeah.
if you were suspended, pulled out that cold weather item on your
Mhm.
thing, that the air would be much smaller.
Yes,
So in effect, if you go out there and you know it's gonna be wintertime, 22 degrees, you gotta expect a bigger air when you're looking at it.
well, although I think if you went ahead and collected enough data in the low temperature regime, and actually ran the model just on that, you would actually get down to pretty small levels. You'd be taking it into account,
Yeah,
okay?
so
But-
that would be kind of-
Yeah. But, so yeah, this is something that can be improved. And, but basically what we have now is a significant improvement. It gets us to, yeah, almost all the time you're gonna be able to put your target in the field of view. So, back up
Hey,
to,
no
yeah,
question.
okay.
So on the modern telescopes, like up at Fan Mountain, I assume all of the stuff is accounted for already on those telescopes, right?
Well, they also run pointing models there. So, but there it's, I think it's automated. You push a button and it gets out there and does its own thing without any human attention, and here it is, okay? Because of the,
The telescope points around the sky now, including German, where it's
wow. So, given, it's a little bit more time consuming and tedious to do it on this scope, but we're doing it. So, anyway.
I think the major difference that I would see probably in your ability to do that really quickly is, you could slew programmatically in both axes and collect a lot of points relatively quickly, right? Whereas this one, yeah, so this one you can slew in right ascension, but then yeah. Yeah.
When did it get fixed?
last year.
Wow, wow. All right, so, just, and Dave, chime in if you have comments here. Yeah, basically, you need two people to do this, at least, somebody to run the camera and somebody, on the scope display, and it's, in, 30 data points a night's about what you can generally manage, I think. And I think we ended up with, we actually didn't average that for all our sessions. I think we ended up with a little less than 60 total points. More would be better. And there was a higher order model that I played with, but it improved things slightly, but I'm not sure it's worth the complexity. So anyway, Dave?
On your, it's something while we got Matt and Ed here, I'm like, try not to monopolize the whole meeting because I'd love to get a brain dump on these guys, but is there a feedback mechanism at all to do basically plate solve on the fly to correct, or is the model, you have sufficient confidence in the pointing model? You mentioned like 0.01 degrees, which is less than an arc minute. You have sufficient confidence in your coordinate pointing models that you don't really need to do any kind of on-the-fly corrections.
Yeah, that's essentially correct.
Okay.
The only air that has to be pulled out of the system is when the whole system is powered down,
Okay.
and you'll find the home sensors, and those things are not accurate.
Okay.
So there's one time I've done my home sensor, look up, go to the sky and say, oh, got to repoint.
Okay.
Adjust the axes, and from there on, it's just night after night. You don't really have to.
Because I wondered, especially when we did that temperature thing, the most obvious thing is maybe there's some differential flexure associated with that temperature. But another thing that I thought about, and I haven't even mentioned it to Tom because the effect could be small, is just the atmospheric refraction in the local weather conditions and, inversions and all stuff like that. And I have no idea what those are like. So maybe they never amount to more than an arc minute or so.
Not that magnitude. Yeah.
What's that?
I don't think it's anywhere near what you saw on that J
Okay.
Yeah.
Okay, you would never see kind of an anomalous weather system that would deflect that much. Okay, all right,
Yeah, pressure change, quite small.
okay,
Change, right, quite small.
okay,
So,
To really see that kind of thing, you've got to have big pressure changes and big altitude changes.
okay,
That's also, you're looking through a slab of atmosphere of different heights.
mm,
That's probably the biggest effect of this temperature.
okay,
And the warning I'll give you real quick is that, there are many differences between June and January that you may not have taken into account. For example, between that time, we lost power up here and had to reboot the computers and start over again. And then the homing that Matt was just talking about, where you find the home positions on the sensors, that may be different enough that what you're seeing is not a temperature offset, but you're actually seeing the encoders being reset, and they just don't reset to exactly the same place they did before.
okay.
oh, that's,
So,
yeah,
And then the other thing that I was gonna ask is something that we haven't talked much about, the tangent arm, which is, were you careful to make sure the tangent arm was in exactly the same place every night? Or did you just?
that's a good point. No, I don't think that we did, and now that, you know,
No.
that definitely, the tangent arm is where the scope is pointing with respect to its
I
axes. So,
expect the tangent arm to be really small.
yeah,
Well, I think in general, because we were not actually adjusting in declination, I don't think it ever deviated very far from zero, because we were just moving,
that's true.
yeah.
Yeah, but the thing is that
Yeah.
on a given night, in June when you were here, the tangent arm was probably set somewhere. And when you came in January, the tangent arm was set someplace else. Now, you do ask observers to set it close to zero again, so that's why I think that's. gonna be-
Yeah, so that latter part, so when we were collecting star fields, it may be better than what I initially thought, because you're right, the procedure says you're supposed to zero out the tangent arm as a part of the closeout procedure. And when we were using the scope, we weren't looking at specific targets. It was basically arbitrarily slewed to a declination, and then, do we see stars? Is there a star field? Basically, are we going to be able to plate solve? And if so, take a picture, and then we just start slewing in right ascension. So it wasn't like we were trying to find a particular target, which might cause us to have to use the tangent arm. So the upshot is we didn't control for that. But if
And I don't
everybody was
think it-
closing out and starting up and zeroing out the tangent arm, we might be okay on that.
So,
I hadn't,
do you, wait for a second.
You know, the biggest error probably with tangent arm is the fact that I had to measure the radius of the tangent.
Yeah.
So we don't really know where the dry system is in terms of radius from the axis.
Okay.
So that gain, the gain that's coming in with the tangent arm correction is almost certainly going to be off by how much. I don't know. We don't have. You know,
so that it suggests a good thing and maybe an intermediate step to do. And all the data from this are freely available. In a nutshell, there's a control panel reading and a corresponding picture of the sky. So that you can start with. Unfortunately, we didn't control for these other things. But what I was thinking along the line, you know, while we were doing it, I said, well, man, it would be really great if I could see what the raw encoder outputs are, you know, because then I could control at least for some of these things. But yeah, okay, all right.
Well,
If I'd known you were doing this, I could have.
Yeah. No, it kind of organically, we were suggested, Tom wanted to improve the tracking of it, and I was frustrated that I couldn't find anything, you know, that I was looking for. So this should be possible in principle to do that. And I think our first foray, we took a bunch of points of where one was, and we took a bunch of points where the, you know, the LCD display was. And I just did a spherical regression, and that actually worked really, really well. But unfortunately, you know, it's hard to interpret that. You know, this thing doesn't map to a misalignment between axes. But I was like, yeah, even that would improve the things. But yeah, I'm anxious to,
Oh,
to engage
so-
with you further at a maybe later time.
Yeah, I definitely want to discuss it further, but do you feel comfortable, though, that this is enough of an improvement to at least start with?
Yeah.
Okay, and so we can talk about how we go about that. And then yes, any other suggestions you have for, we can always revisit this and improve it.
Take a question?
For me, is offset in the optical axis. So for those that don't know, in 2018, we removed the lens from the telescope completely, disassembled it, cleaned everything thoroughly, reassembled it, put it back on the telescope. But we were very careful to try and put it back on exactly as we found it,
Mhm.
knowing that if there was a misalignment then, that we would be putting the misalignment back in with the goal that we would get around to measuring the alignment of the lens and then
Mhm.
trying to fix for that in the future.
Mhm.
And not right, 7 years later, we still haven't gotten around to doing that.
Okay.
But that's another correction that I think would be really cool to look at is there are other ways to measure the alignment of the lens
Yes.
and get that fixed first.
Mhm.
Because the problem is if we incorporate this model and then go tilt the lens a little bit.
Then it's
then-
invalid and we have to do it again.
Do you know what the magnitude, you mentioned that the lens could be off. Do you know the extent of the declination tangent arm? I think Tom mentioned 30 arc minutes for a misalignment of the optical axis, I believe. I can't remember. It's 20 or 30.
Yeah, it was about.
But,
30 arc
that could impossible be due to the deck.
Lens up there being tilted.
Yeah, but
Yeah,
I'm saying, could we be conflating that with a not controlled for tangent arm setting?
Well, no, that was the misalignment in the direction of
The declin.
of right ascension.
Oh,
Okay, and it was the right,
That might be
and
this
the
one, right?
sidereal rotation, and then the hour angle encoder
Oh,
was
yeah.
apparently offsetting. So it's not,
I guess
that's
it
not
was
a,
this one here.
that's not a,
What's that
yeah,
one?
yeah.
All right,
So-
okay. All right.
So anyway,
Question?
I think
Question?
there seems to be enough of a benefit. So, but yeah, so we maybe collect more data in the future to try and improve it some more, so.
Can you take a
Thank you.
question?
I hope it is.
Yeah.
Yeah, it's worth mentioning that, it's really cool. Thank you very much for doing this because this is something we just haven't had the time to do on this telescope, in large part because of the way this telescope is used. Down at Fan Mountain, we're using the telescopes with digital cameras that have small fields of view, exactly the problem you were mentioning. And because the 31-inch, and Matt's, we use the term repair, but I really want to give Matt credit for this. It was truly an upgrade. The 31-inch was a manually operated telescope, and Matt has turned it into a fully automated robotic telescope over the last, and I would say 2 years, really.
I had to rebuild both,
Wow.
the access drives,
Oh, okay.
from the ground.
But that's what's necessary to use digital cameras today. You really can't be using digital cameras on a telescope like this without the models and things put in there. But we haven't bothered to do it here because we haven't been using the telescope that way.
Yeah, I mean, at one point I thought, well, geez, if we could only piggyback another scope with the digital camera.
Yeah.
I can tell where the heck it's pointed and I can correct for that. But yeah, it's.
Maybe a future topic of discussion, I'm curious about the issue we had with your attempt at doing a declination slew motor years back. And, I'm wondering if maybe we can revisit that and see if there's might be a solution to that. Because then that would open up doors.
Yes, but I will tell you this, that, my opinion for the 26-inch, I know exactly where you're going with this, Tom. I want to go in exactly the opposite direction. This is a historically significant out-of-park telescope. I know how lots of people use this telescope and I want to make it as usable as possible, but if I could have my dream world, we pull everything off and go back to the way it was in 1885 to restore, because it's one of the few.
Including
Yeah.
the weight descending.
Yeah, exactly, absolutely.
Yeah.
So for people that don't know, this is the largest Clark telescope on a Clark mount that exists in the world. Alvin Clark built bigger telescopes, but they're all on Warner and Swayze mounts. So
Okay.
this is the finest example of his work, top to bottom. And I really love, in an ideal world where we have an infinite amount of money and an infinite amount of time, take this telescope back to what it was in 1885. And then for people who want to do digital imaging and stuff, I can get you access to a 24-inch fan mount that'll,